Good afternoon, everyone. So myself Rhithick, and I'm from NIT Trichy, and my teammate who worked on this topic along beside me is Vivek. And so our research topic is lightweight certificateless digital signature scheme for wireless sensor network. Yeah. So in this current technological era, a lot of smart objects have been emerged. So like wireless sensor networks deployed everywhere in the environment to collect data regarding the surroundings and everything. So how do we ensure the security of them when they are connected to the public network? Well, that's where cryptography comes in. So encryption and digital signatures ensure authentication, integrity, and confidentiality. For example, let's take most frequently used terms in cryptography: private keys and public keys. So these are the keys that are mathematically derived, so that like if the message is encrypted with one key, only the counterpart could be able to decrypt it, right? And this is an example of how do we ensure the digital signature. It's a process for digital signature. Like if a sender wants to send a message, alongside the message they append the signed message digest, so that uh, that message digest is actually encrypted with the sender's private key. Okay, the private key is not known anywhere, only the sender will know about it. And in the receiver, they use the sender's public key to decrypt the signed hash message, and then they also find the digest of the received message. If they compare and the message is equal, then we know that the message has not been tampered, and we know the authenticity. Like it's it came from the sender only. Nobody has been impersonating that, because we use the sender's public key. So this whole system is called is involved in asymmetric encryption, and there is also symmetric encryption, in which while encrypting and decrypting we use the same key. One of the problems in the symmetric encryption is the key sharing. We do not know, like if we want to share the key, it would be difficult without others in the network knowing about it, right? So little background about elliptic curve cryptography. It is also a method of cryptography in which the keys are the coordinates of the elliptic curve. So why have we used ECC in our work? It's not. It's so our work is involved with wireless sensor networks. So when you think about it, they are lightweight. They need less resources and less computational uh, power, right? So ECC could achieve 160, like ECC could achieve the security of what RSA could achieve in 1024-bit key length in just 160 bits. So obviously, if we could achieve the same security in smaller number of bits, that makes it lightweight. Why not go with it? So this is the general equation of elliptic curve, and I'll I'll show you. I'll just tell you about an example of key sharing using elliptic curve, just to get clear with it. So there are two persons, Alice and Bob. Alice wants to their goal is to derive at the same shared key without others not knowing about it. So Alice sends her public key QA to Bob, and Bob sends his public key QB to Alice. Now what they do is they multiply their the received key along with their respective private keys, and we arrive at D8, the shared key. Okay. Now let's say a man in the middle acquires QB, and let's say he knows the curve. So the generator point is fixed for a curve, right? So if I know QB and if I know G, why can't I obtain DB? That is where the ECDLP problem, elliptic curve discrete logarithmic problem, comes in. So it is nearly impossible to find DB provided QB and G. The only way is brute force, and that will take really long time. So coming to our topic, what is the existing problem? So we are in the existing traditional scheme, they use certificates for authentication, which is really resource computationally, like they are expensive, and uh, it requires more resources in general. Okay, and then they move on to ID based cryptography. So in this there exists a third party which is called PKG, public key generator. uh, they distribute private and public keys to each nodes in the network. Again, there is a problem in this that is called key escrow problem. This is basically nothing but a single point of failure. If the PKG, that is the third party, is compromised, the whole system will be compromised. So we move on to the improvised version of that, that is certificateless signature scheme. In addition to the existing ID based cryptography, each node in the network generates its own partial private and public keys, so that like even if one key is compromised, like uh, together of user generated and third party generated forms a key. So we need both keys to be to compromise a node. And if you are not careful with this proper algorithm, if the algorithm is weak, then it is vulnerable against security attacks. So our goal here is to develop a digital signature scheme that is lightweight and requires less sign time and verify time. In doing so, we should not compromise the security provided. Like we should have fast like sign and verification time, but at the same time it should have the same amount of security. So this is the system model. There is there are three different entities: KGC, signer node, and verifier node. So each node in the network sends its unique ID to the KGC, and in return they get a value called D. Then the signer node follows these steps to generate a signature, and that signature is sent to the verifier. Now what verifier needs to do is, verifier needs to follow this verification equation, and if the left hand side is equal to the right hand side, then the verification is success, and we are like the signer node is authenticated. So in this, if we compare the results, if you could see the sign time, there's not much of a change, right? Because we can't reduce it anymore further. That is the least possible. If you see the sign time operation, the minimum operation is TSM. Like SM implies scalar multiplication, each operation. So we can't drill down further into this, reducing it. But if you see the verification time, we can reduce it further, and our proposed algorithm is fastest among the existing CLS schemes. But if you see the CLS scheme that is existing prior to our proposed algorithm, Tamburitals, that is also fastest, but if you see their security, they are insecure against type 1 attacks. But our algorithm is also secure against both attacks. At the same time, if you see the basic mathematical operations is also equal to Tamburitals. So what we conclude is, using ECC to make the system lightweight is helpful, and then our proposed scheme is 28% faster than existing CLS schemes. Not to mention the security is also it's secure against several adversary attacks. And in future we intend to perform this scheme in real life WSNs, like and then measure the energy, and thank you. Any questions? Sorry? Yeah, so the algorithm is written like it is a modified See, if you see there, the final signing algorithm is the last one, where V is equal to x inverse d plus h2 into u mod q, that is. And in order to derive that, these are the operations performed. Like, one randomly chosen variable is taken, and then the input from kgc also taken. So if you see this, how do you point the list? Okay, it's fine. If you see this, this is the time. That is the operation of scalar multiplications, where p is the coordinates of the elliptic curve, and the small x is a randomly chosen value.
See, the last step you said an operation less.
Yes, sir.
3 just 4. What is the last?
3.
3. Can you just indicate why that one? Where did you say?
Yeah, sure. So basically we reduce one hash operation. So in the verification, like, there is, yeah. So this is one scalar multiplication, and then this is one scalar multiplication, and this is one scalar multiplication. So we took 3 scalar multiplications, but in one of the previous algorithms, there will be another hash function, like there is a plus another term. So we remove that scalar multiplication operation.
Last term.
Yes. No, not just the last term, and the algorithm itself is different. So if you reduce the hash function, you have to change the entire algorithm, because other variables are also dependent on that hash function.
How it is certificate less scheme, because if no trust authority is involved, then how other party will trust on your algorithm?
Yeah, we don't use certificates, um, but yeah, we use the keys, right? Like, if the uh, verification is successful in, like, if whatever I compute from the network, the public parameters provided, and whatever you send matches, then what's wrong in that? Like, if it's mathematically proven, so it will be difficult to impersonate that.
So I have a question. Like in normal public infrastructure, right? We have a CA. So CA is issuing the certificate to both the entities.
Hmm.
But in this scenario, you don't need a third party like a CA who issues the certificate.
Yes.
Then how will you ensure the authenticity of the certificate?
Yeah, so this KGC sends partial private keys for each nodes in the network.
But there is no stamping of any authority involved in third party. That is the case, because it is just agreement between the two parties.
Hmm.
That I realize on your key and you realize on me. So that's all.
Okay, I get it.
So we can ensure the confidentiality of the thing, right? But there is no third party authority who says, okay, these two parties who were communicating between each other,
Hmm.
they are authentic. So there should be third party to ensure it, right?
Yeah, but if we do that again, we are just increasing the resources on them, right? Like, it's,
As per code, there is no sanctity on the issuance of such keys based.
okay. Okay, sure. I will look up on them as well.
Some kind of identity tying to the public key
Hmm.
is required in all these systems.
Sorry, sir.
Tying the identity to the public key,
Huh.
whether it is ECC or RSA and everything,
Huh.
that is still required.
Yes.
See how, I mean, that can be,
Okay.
should be incorporated with that efficiency also, with no overheads.
Yeah, sure. Anything else? This is my first presentation, so I'm a little nervous. Yeah. So yeah, thank you.